So let's look again at the periodic table and think about those orbitals as we do it. So remember, and you can go back and reference the other slide if you'd like, but we start off with the 1s orbital with 2 electrons. So 1s with 2 electrons, 1, 2. Hydrogen and helium are the ones that are a little different. We then have the 2s orbital, and then following that was 2p with 6 electrons, and then 3s, and you can go look at the order on the list, and it'll be the same as this, and 3p, because this is how I remember the order of everything. 4s, s's, 3d, and then 4p is over here, and so on. When you get to the f orbitals, those are the ones that are down here. So the periodic table, the setup of the periodic table, not only shows you all of the other things that we've talked about before, about where the metals are, the nonmetals, the groups and periods and all of those things, but it literally shows you where each of the electrons are and how the electrons fill up inside of those shells. And so we can use the periodic table to figure out what's the highest shell that's unfilled in any element. And so, for example, the only other thing that's different is that the atoms pair up in a particular way. And so we can figure out what shell they're on and how that in terms of finding all of the structures of these atoms. But the main thing I wanted you to see was that it directly relates to what you have here in the periodic table. We can use what's called electron dot structure notation. This is sometimes written slightly different when you're dealing with the chemistry of the elements. Talk about the upper shell of each of these elements. And because of this, we can determine a lot about the number of electrons in the upper shell, like I was just saying. And this tells us a lot about the different groups inside the periodic table. Notice the alkali metals with 1 electron floating around all by itself. And the halogens that are only missing 1 electron. And so we can actually look at this. The inert gases on the periodic table, they hold really tightly to their electrons because all their shells are full. They're all here on the final row. With all of their full shells, they don't like to gain or lose electrons. They hold onto those electrons really tightly, so they don't really chemically react. They don't really do anything chemically. They don't form compounds. They just hang out with full electron shells. Alkali metals, including hydrogen, they'll have that 1 extra electron. Hydrogen is just 1 proton and 1 electron. If that electron can get easily removed, then you wind up with a positively charged ion. It's lost an electron. All of these can have a charge of +1 very easily. They can very easily lose that electron. Most often, they lose that electron to the halogens. The halogens have nearly full shells. And so they can easily catch an electron from somewhere and form a negative ion. And these will mostly have charges of -1. And then finally, if we look at these transition metals in the middle here, these are all going to have multiple electrons in their upper shells, right? The upper shell itself can hold 10 electrons, lots of empty electrons, lots of electrons to run around inside of those upper shells that can react chemically. All of those extra electrons give metals their properties. If you watch one of the videos that I posted a few weeks ago, um, they make a mention of the most common elements that are going to be magnetic right around in here. Iron being one of the main ones. And they're right around in there because that's the smallest atoms with the most extra electrons laying around. So those electrons could line up in the right particular way inside of those metals as they cool and become magnets. And now that we kind of understand how all of these things interact based on their usage and the number of electrons that they have, in the next two sections, we're going to talk about how the electrons allow them to form into different types of substances.